In this presentation, I will talk about Probit and Logit models. The outline of this presentation will be first to discuss the linear probability model, then discuss the features of the Probit and Logit models, then talk about maximum likelihood estimation, the coefficients, the predicted probabilities, and marginal effects, including marginal effects at the means and average marginal effects, and finish up with goodness of fit measures, including pseudo R-squared and percent correctly predicted. So what is a binary dependent variable? That's a variable that has two outcomes, and it's conventional to denote them as either 0 or 1. Examples include a variable such as whether a person is working or not working, whether a person has insurance or does not have insurance, and so forth. Typically, the outcome of interest is denoted as 1 and the other outcome is denoted as 0. So y would be equal to 1 if working and y would be equal to 0 if not working. However, sometimes if the outcome of not working is of interest, then it would be denoted as 1. So here we would have y equals 1 if not working, y equals 0 if working. So it's not necessary that the 1 is always the positive outcome and the 0 is always the negative outcome. Here we may be interested if someone is not working, for example, because they may be qualifying for unemployment benefits. And so that's why we could have y equals 1 if a person is not working. But typically, the outcome of interest is the outcome that a person is working or has insurance or makes a purchase and so forth. Also, there's typically fewer outcomes of interest. In other words, there are fewer ones in the data than zeros, although that's not necessarily always the case, but typically there are fewer ones in the data. Now, what is the linear probability model? A linear probability model is a linear regression model where the dependent variable is a binary variable. So this is exactly as we have talked about a linear regression model, only that the dependent variable is a binary dependent variable that takes the values of y equals 0 or 1. And so here we have y equals, and then we have all of the independent variables, x1, x2, all the way to xk, plus the error term here. And these beta 0, beta 1, beta 2, and beta k are the parameters here. And so we can either express the linear regression model like that, or for the first time, we are going to be expressing all of this beta times x, the summation of it, as x times beta. So we would be using a matrix form. So when we say x times beta, that means beta 0 plus beta 1 times x1 plus beta 2 times x2 and so forth. And this is the matrix form of it. So it's like the same thing, but a shortcut notation for it. So now, if we have this as the expression, what is the expected value of y? Well, that is the expected value of y would be equal to x beta plus the expected value of u. And we know that the expected value of the error term is equal to 0 because of zero conditional mean. So the expected value of y is actually x beta. But now we also know that y is a binary variable that has two outcomes, 0 or 1. So the expected value of y is the same as the probability of y equals 1. So let's look into it a little bit more carefully. Here we have the expected value of y is equal to 1. So basically, if y is equal to 1 times the probability of y being 1 plus 0, so basically if y is equal to 0 times the probability of y equals 0. So because this expression here is multiplied by 0 and this one is multiplied by 1, that would be equal to the probability of y equals 1. And, again, thinking about it, that makes sense because the expected value is what is the chance that y would be equal to 1 times the 1 that y is being equal to, and then what's the chance that y would be equal to 0 times 0? So that would be the probability of y equals 1. To think about it in other terms, if 30% of the y's are ones and the rest is 0, so basically 70% of the sample is 0 and 30% are 1, then the expected value of y, if we just take an average of this variable here, that with 30% there are ones and 70% are 0, that the average of that would be 0.3, but that would also be equal to the probability of y equals 1, and that is 30%. So basically, if we do not know um, the value of y for a particular person I in the sample, we can say that with 30% probability, that value would be a 1. So all of these things mean the same thing. So because of that, and because the average or the expected value of y is the same as the probability of y equals 1, the linear probability model for the probability of the outcome y equals 1 is the probability of y equals 1 equals x beta. So basically here, instead of just saying y is equal to x beta, we would say that the probability of y equals 1 is equal to x beta. Now our dependent variable would be interpreted as not y, but the probability of y being equal to 1, and that would be equal to x beta. So this would be a linear probability model, and the way it's estimated is basically like a normal regression model where y is the dependent variable and all the x's are independent variable, but the interpretation of these coefficients would be that that would be the effect of x on the probability of y equals 1 rather than the effect of x on y. Okay, so what are the advantages and disadvantages of the linear probability model? The advantages are it's very easy to estimate. It's a linear regression model, so we know how to do that. And it's very easy to interpret because the coefficients are the same as the marginal effects. And also the coefficients and predictions are reasonably good for the majority of the cases. So these are the advantages. The disadvantages of the linear probability model is that it's not the best model for a binary dependent variable. So Probit or Logit models are better and they're preferred, and many people would be using a Probit and Logit model instead if the dependent variable is a 0-1 binary variable. The predicted probabilities in a linear probability model can also be less than 0 or greater than 1, and that's a problem because the probability needs to be between 0 and 1. Here, the linear probability model could give the wrong prediction of probabilities that are less than 0 or greater than 1. The marginal effects are the coefficients, so that is an advantage because it's very simple, but the problem is that they're constant. In other words, they do not vary with x, so we have constant marginal effects for any value of x, and that's also problematic. And the final disadvantage of the linear probability model is that there is heteroscedasticity because the variance of the error term is not constant. So here how we have the variance of y, here's the variance of the dependent variable, and that is basically with two outcomes. That's the probability of y equals 1 times the probability of y equals 0, or that basically is the 1 minus the probability of y equals 1. So because these expressions actually depend on x, basically we would see heteroscedasticity for the linear probability model, and that is a disadvantage. Now, because the linear probability model, basically ignoring the fact that the dependent variable is a 0, 1 variable and estimating a linear model with it, we would be looking for better models. So here is again the linear probability model that estimates the probability of y equals 1 as a linear function of the independent variables. So this is what I had on the previous slides. The probability of y equals 1 equals, and here we have again all the coefficients. We have the x variables, or in a matrix form, we have x times beta. Now, the Probit and Logit models would estimate the same probability of y equals 1 as a nonlinear function g of the independent variables. So here I have almost the same expression where it's the probability of y equals 1, but instead of just having this function here, x beta, I have g, a function of this expression here. Or the shortcut notation here would be g of x beta. So now this g function here would be a nonlinear function that transforms this x beta to be between 0 and 1. And we need that because this probability of y equals 1 is a probability, so it needs to be bounded between 0 and 1. So this g function again picks up any number here, x beta, which could be from minus infinity to plus infinity, and transforms that number, whatever that number is, to another number that is between 0 and 1. So we can actually interpret that as probability. Okay, so now let's talk about the normal distribution and what is the PDF and the CDF of the normal distribution. The probability density function of the normal distribution, denoted as phi, that shows the probability that y is between two numbers. So this is the PDF of the standard normal distribution, and you recognize this as the bell-shaped curve, the standard normal distribution, the probability density function of it. And so what we have here is basically here's for any value. Here we could say what is the probability that um, uh, it's between two numbers. So for example, we know that 95% of the observations are between minus 1.96 and plus 1.96. So this is the PDF of the normal distribution. On the other hand, the cumulative density function, or CDF, of the normal distribution, this is the capital phi, shows the probability that y is less than a given number. So this CDF basically accumulates all of the values here, and it's basically a number between 0 and here it's the maximum number is 1, so it's a number between 0 and 1. So here if we have this what is the chance that y would be less than 0 here in this case? Well, this is exactly 50% from here on. And what's the chance that y would be less than a very, very large number? Well, that would almost be a chance of 1, and so forth. So this CDF is basically a very good candidate for one of these g functions because it gives, if you take any number here, it would transform it to a value that is between 0 and 1. So that's a good candidate for this g function that we talked about. So this is what the Probit model does. The Probit model uses the cumulative density function, the CDF of the normal distribution phi. So when we had here the probability of y equals 1 is equal to a function g of x beta, that function g now would be the CDF of the normal distribution here. And the CDF of the normal distribution has also this expression. But the nice property of using the CDF is that give any number from minus infinity to plus infinity, and this phi function, the CDF, would transform it to a number that is between 0 and 1. And this is important because, again, we have a probability of y equals 1. So we need to have a number that is between 0 and 1. And that's what the CDF of the uh, normal distribution does. And so here, again, for the Probit model, we have probability of y equals 1 equals the CDF of the normal distribution of x beta. And that's how a Probit model would look like. The logit model, on the other hand, uses the logistic function. So here, the probability of y equals 1 would be equal to g, a function that transforms x beta into a number that's between 0 and 1. And that logistic function would take the form like that. Exponent of x beta divided by 1 plus the exponent of x beta. So this exponent of x beta is the same as e to the power of x beta divided by 1 plus e to the power of x beta. So this exponent here is the same as e to the power of x beta. So now let's look at this expression here and kind of confirm that that would be a number between 0 and 1. And that is the case because this exponent of x beta is positive. So think about it this way. If, for example, this x beta is it's a negative number, like tending toward minus infinity. So what we are going to have here is this would be a close to 0 number. This would be a close to 0 number. So here we would have the overall expression being close to 0. On the other hand, if x beta tends toward infinity, here we would have a very large number divided by 1 plus a very large number. So that expression would be tending toward 1. And so because, again, this exponent of x beta is a positive number, this expression would actually ensure that we have the probability of y equals 1 being bounded between 0 and 1. And that's a good thing because we have a probability. Okay, so now if we have, this would be the expression for the probability of y equals 1. What is the expression for the probability of y equals 0? Well, the probability of y equals 0 would be equal to 1 minus the probability of y equals 1 because there are only two cases here, either y is equal to 0 or y is equal to 1, and these two probabilities need to sum up to 1. So this is why we have the probability of y equals 0 equals 1 minus the probability of y equals 1. And then we are substituting this expression here with the probability of y equals 1. And then we're putting everything under a common denominator, and we have this is actually the expression for the probability of y equals 0. So now let's check if we actually sum up this expression with this expression. You see how the numerator and denominator are going to be the same if we sum them up, and this expression is going to be equal to 1. So it makes sense that the probability of y equals 0 plus the probability of y equals 1 would sum up to 1. So anyway, so now we talked about how the logit model uses the logistic function for its model. And here we have the probability of y equals 1 equals exponent of x beta divided by 1 plus the exponent of x beta. So this is how this model would look like. These beta here are still going to be coefficients, but it's a bit more complex function here because now we have a nonlinear function in the parameters. So the way we had the linear probability model being linear function, linear model in the parameters, we no longer have that. That's the nonlinear model that we have now. Okay, so switching gears now, let's talk about what is likelihood and likelihood function. So the word likelihood is the same as the word probability in English. So if we say likelihood, it's the same as probability. And the likelihood is basically a probability that the outcome for a particular observation I in the sample would be yi. So here we would say the likelihood or the probability of yi being equal to 1 is basically the probability of the yi equals 1. The likelihood of y equals 0 would be the probability that y would be equal to 0. So this is almost like a definition where what's the likelihood or probability of y equals 1? Well, that is the probability of y equals 1. And what is the likelihood or the probability that y would be equal to 0? Well, that is the probability that y would be equal to 0. It's almost like a definition. Okay, so now let's propose that we use this likelihood function that is defined as such. Here we have the probability of y equals 1 to the power of y times the probability of y equals 0 to the power of 1 minus I. So this is called the likelihood function. So let's check that it works for both of the outcomes that we have. So now, what is the likelihood or what is the probability that y would be equal to 1? Well, let's replace in this function here y being equal to 1. So here we have the probability of y equals 1 to the power of 1 times the probability of y equals to 1 minus y, but this y is equal to 1. So here we would have to the power of 0, this expression would be equal to 1. And so we would have basically the probability of y equals 1. By the same logic, we have what is the likelihood that y would be equal to 0? Well, we would replace here y equals to 0 and here y equals to 0. So here we have the probability of y equals 1 to the power of 0 times the probability of y equals 0 to the power of 1 minus 0. And so this expression, because it's to the power of 0, would be a 1. And here we would basically have the probability of y equals 0. So now the nice thing about this likelihood function that we have is that it combines both of the outcomes of y equals 0 and y equals 1, such that it's basically giving you the likelihood that y would be whatever we observe it to be. So if y is equal to 1, that function would give you the probability of y equals 1. If y is equal to 0, that will give you the likelihood or the probability that y would be equal to 0. So this is why it's still a likelihood function, but it combines both outcomes and it works for both of them. Okay, so now why do we need such complex functional form for the likelihood function? So let's start with this likelihood function that we talked about on the previous slide here. And what we're going to do is we're going to take logs of it, and then we would sum it up over all the observations. So if you take a log of an expression to the power of y, what we would have is a log of something to the power of y would be y times the log of this expression. And if we have multiplication here and we're taking logs of it, if you're taking logs of it, that would be here with a plus sign. And so here would be this multiplication would be a plus. And then if you take logs of this, we would have 1 minus y, which is here, times the log of this probability of y equals 0. So here's what we are doing. We're taking basically the logs of this expression and we're summing it up over all the i's, over all of the observations. So now we're almost done. One more step. The final step would be to substitute probability of y equals 1 equals g of x beta. This is basically our functional forms that we talked about. And this g function could be either for the Probit model or for the Logit model, depending on what this g function is. And so if we substitute this g function into the log likelihood function above, here's what we are going to have. So here the probability of y equals 1, we are going to replace this with g of x beta. And the probability of y equals 0 would be 1 minus the probability of y equals 1, and that is the probability of y equals 1. Okay, so now we have an expression that actually is a function of these beta coefficients. And so basically we can find these coefficients by maximizing the log likelihood function, and that's how we are going to be finding these beta coefficients that we have here. Okay, let's discuss this a little bit more. This what we call here a maximum likelihood estimation. So what we're doing here, we're maximizing the likelihood function. So the Probit and Logit model coefficients would be obtained by maximizing the log likelihood function. This is the log likelihood function that we talked about on the previous slide, and here we're maximizing this log likelihood function. So if the outcome yi is equal to 1, so if a particular person has the actual outcome of being 1, then the predicted probability P of y equals 1 is maximized. So basically, as we're searching for this beta coefficients, we want this probability to be maximized. In other words, we want to receive a number like 0.8, 0.9, very, very high number, certainly above 0.5. And so that's how we're going to be maximizing this likelihood function. So if y is equal to 1, we want this expression to be as high as possible, the probability of y equals 1. On the other hand, if the outcome is 0, the probability of y equals 0 should be maximized, or equivalently, we want the predicted probability P of y equals 1 to be minimized. So what we would want is that probability of y equals 1 to be a very small number, like a 0.1 or 0.2, definitely less than 0.5. And so this would also be maximizing this function. So if we maximize this function, what we want is, if y is equal to 0, we want this number to be as high as possible. So basically, the probability of y equals 1 to be as small as possible. And if y is equal to 1 here, we want the probability of y equals 1 to be as high as possible. And this is how any computer software is searching for these coefficients. We're starting with the default expression where all of the coefficients are equal to 0. And basically, we're trying to move away from this and find the actual coefficients that would maximize this likelihood function. And this is the approach that we're using. So if we use this maximum likelihood estimation, the nice property is that these maximum likelihood estimators are consistent, asymptotically normal, and asymptotically efficient if all of the assumptions hold. So they have all of the nice properties of the estimators that we have seen so far, like the OLS estimators. Okay, so now if I repeat this one more time of the Probit and Logit model coefficients, how they're obtained by maximizing the log likelihood function. Basically, if the outcome is equal to 1, we want that the predicted probability of P of y equals 1 to be maximized. Now, compare and contrast this with how the OLS coefficients are obtained. They are obtained by minimizing the sum of squared residuals. So here we're minimizing the sum of the squared residuals. Or basically what we have here is the difference between the actual and the predicted values y hat. And here, by replacing this predicted values with this expression here, x beta hat, we are basically going to be solving these equations for and to find these parameters beta. So again, these are two different methods via which we obtain coefficients. The OLS coefficients are minimizing the sum of squared residuals, or basically the difference between the actual and predicted values. Whereas here, what we're doing with the maximum likelihood estimation is we want to be maximizing the likelihood that y would be equal to 1 if we see that y is equal to 1 in the sample. That's the method via which we find coefficients. Okay, so now let's give you an example. So here we have data and we want to model and that explains if women are in the labor force or not. Basically, if women are working or not. And so here we have in labor force, that would be in labor force would be a binary 0, 1 variable for whether women are in the labor force or not. So basically whether women work or not. And here we have several independent variables. This is the non-wife income. This is obviously education, experience, the age of the person, and this is kids that are less than 6 years old, the number of kids that are less than 6 years old. So now we want to we want to explain if women are working or not, depending on their characteristics. So basically, their education, experience, age, their other household income, and whether or not they have young kids at home. So the models that we would be considered is what is the probability that a person would be in labor force, and that's going to be a nonlinear function of nonlinear function of all of these variables that we have here. So if you look at summary statistics of the data, so these are the different, this is the dependent variable in labor force, and these are all of the independent variables. And here we have mean, standard deviation, min, and max. And again, look at in labor force, we have minimum of 0, maximum of 1. So that's our 0, 1 variable. And here the average is 0.57. So what this average means is that 57% of the women are in the labor force and the rest are not. So 57% of the women are working and the rest are not. So what we are calling here is that the unconditional probability of being in the labor force is 0.57, or in other words, that the probability of y equals 1 is 0.57. So we're calling this unconditional probability because if we don't know anything about a particular person in the sample, we would say that with probability of 57%, this person would be working. Now, if we know something about the person, depending on what's their education, experience, whether or not they have young kids, we would start to modify this probability to give it higher or lower probability of them working, depending on the results and the estimated coefficients of our model. Okay, so if we now estimate the linear probability model, the Probit and the Logit model, these are the coefficients that we are going to get here. So here, this may look like this is the linear probability model. So this looks like a normal regression. Here, the dependent variable is in labor force, and these are all of the independent variables, and these are the coefficients that we have here using the linear probability model. So basically, that's a regular regression, and these coefficients that we have here, they're obtained using by minimizing the sum of squared residuals. How we know that? However, for the Probit and Logit model, how we find these coefficients is by maximizing the log likelihood. And if you look at the output, the statistical output from the software package, you will typically see how we start from a base log likelihood, and that's basically if all of these coefficients are equal to 0. And then we would try to improve by maximizing this log likelihood function, and that's how we are going to be finding these coefficients. And so when we find the absolute maximum of the log likelihood, that's when the software is going to stop and it's going to give us the coefficients. So this is how these coefficients are obtained. So they do look like coefficients, but they're obtained from them by maximizing the log likelihood function. So one thing to notice here is that the coefficients between the Probit and the Logit models differ, and this is because of the functional forms of this Probit and Logit model. So remember, the Probit model uses the CDF of the normal distribution, whereas the Logit model uses the logistic function. And so these coefficients are different from each other because of the different g functions that we're using. So here the logit coefficients are about 1.6 times the probit coefficients. So these coefficients are about 1.6 times the probit coefficients, and that would almost always be the case. So now, how do we interpret the coefficient on education? Say this coefficient here. So the way to interpret it is if we see that they are significantly different from zero, we can interpret them as women with higher education, so more years of education, are more likely to be in the labor force. So this is how we would interpret this. Here, if we have a negative significant coefficient, the way we are going to interpret it is that women who are older, so basically if their age is higher, they would be less likely to be in the labor force. So we use the words more likely and less likely because now we have a probability of in labor force being equal to 1 as a dependent variable. So our dependent variable is not in the labor force itself, but it's the what we're trying to well, that's the dependent variable, but what we're trying to explain here is the probability of being in the labor force. So that's why we're trying to express and explain the likelihood of them being in the labor force. And this is why we want to say higher probability to be in the labor force or lower probability to be in the labor force. So we cannot interpret the magnitudes of these coefficients, and one of the reasons for that is that the coefficients are not the marginal effects, and they do differ between the Probit and Logit models. So it would be incorrect to interpret any of these numbers when by definition these are 1.6 times of these coefficients. So we cannot interpret the magnitude. The only thing that we can say is more likely or less likely as we're looking at coefficient, just the direction of the effect. Now, sometimes I see wrong ways of interpreting these coefficients. For example, people would say that women with higher education are likely to be in the labor force. That would be incorrect because, for example, if the maybe the unconditional probability is low in the sample. We don't have that here, but if say the average uh, let's say women are in the labor force with 20% probability. Well, they're not going to be likely to be in the labor force. So that's why we cannot say likely. We have to say more likely or less likely. We also cannot interpret that as they are somehow more in the labor force, as if more is in terms of more hours. So make sure that you use the word more likely and less likely when you interpret coefficients here. So this is the most that we can do as far as interpreting coefficients. Again, we just interpret the direction of it, more likely, less likely, but not the magnitude of them. Now, let's switch gears and talk about predicted probabilities. So after estimating the models and obtaining the coefficients beta hat, the predicted probabilities can be calculated as this. So the probability of y equals 1, here we have the g function, depending on the probit or the logit model. And here we can actually plug in the estimated coefficients into this formula, and we could be obtaining g of x beta hat. So now, if the actual value is equal to 1 and the predicted probability of y equals 1 is above 0.5, that would be a correct prediction. If the actual value y is equal to 0 and the predicted probability of y equals 1 is below 0.5, that's also going to be a correct prediction, because if we have the actual value being 0 and we're giving it a very low probability that it's going to be a 1, that would be a correct prediction. Otherwise, these are going to be incorrect prediction. And so the average of these predicted probabilities will be actually the unconditional probability, which is the sample average y y bar. Okay, so here's the example, and this is the data set that we have. And here I have put the first four observations and then observations from 601 to 605. So these are the actual values for the in labor force y variable that we have. So observations from 1 to 4 are in the labor force, and these observations that we have here are not in the labor force. So after, so we estimate the predicted probability from the linear probability model. So this is in labor force hat for the linear probability model. And what we see here, this is the same as the y hat that we had before. So here the y hat, this is the same as y hat. Here, the predicted probabilities that we have for the Probit and the Logit model is what is the probability that y would be equal to 1. And now, if basically any of these numbers are above zero point 0.5, we would say that we are predicting that this person would be working, would be in the labor force. And if that probability is less than 0.05, we would be predicting that this person is not working. Okay, so let's notice a few things here in this table. So first of all, for the linear probability model, the predicted probability can be a negative number, like this minus 0.19 for observation 605. So this is a problematic number because a probability needs to be between 0 and 1. So now we have definitely a wrong prediction for the predicted probabilities. And this is one of the issues and one of the disadvantages that we have of the linear probability model. It could also show you a number that is above 1, and that is not reasonable. So now let's look for the Probit and Logit model. The predicted probabilities for the first four observations. Here we know that the actual value of y is equal to 1. So we know that this person is in the labor force, that person is working. And if you notice here, the predicted probabilities here are all above 0.5. So the model actually made the correct prediction because we know that these first four people are in the labor force, and the model is now predicting the probability of them being in the labor force is greater than 0.5. So the model is making the correct prediction. Now, for the for the people here that are not working, so they have 0 as the actual value, they're not in the labor force. What our model is showing here for the probability of y equals 1 here is very low, so this is less than 0.5. So these are the correct prediction because this person is not working here, and we are predicting only a 30% chance that they're going to be working, or a 29% chance that they're going to be working. So this is actually a correct prediction because that person indeed is not working. However, for this person here that is not working, for some reason the model is giving very high probability of almost 70% that the person would be working. So right here, this actually is not a correct prediction right here for this person because they're not working, and we're assigning it a very high probability that it's going to be working. And so another thing to find is that if we're to calculate the average here, that's going to be if we're to calculate the average here, that's going to be 0.57, which is basically this is the probability that someone would be working, or 57% of the people in the sample people in the sample working, being in the labor force. So if we calculate the predicted probability for here, if we sum up all of the predicted probability and we find the average of these predicted probabilities for these models, we would also find actually that that is 0.57. So the average of all of these predicted probabilities would be 0.57, and that would be the same as the average of the proportion of people that are in the labor force. Okay, so we talked about the coefficients. We talked about the predicted probabilities. Now we're going to talk about marginal effects. And the reason why we talk about marginal effects is that sometimes the coefficients are not the marginal effects. And so let's discuss this a little bit more in details. In the linear probability model that we have here, so we have the probability of y equals 1 equals x beta. So here, the coefficient on xj would be beta j. We're working here with generic coefficients. So what we are saying is that the coefficient on x1 is beta 1, the coefficient on x2 is beta 2, the coefficient on xk is beta k. So we're working with each and any of these coefficients here. So this is a more generic notation that we have here. So what is the marginal effect of xj on the probability that y would be equal to 1? So this would be, for the linear probability model, that would be beta j, because if we take the change in the probability of y equals 1 divided by the change in xj, this will be equal to beta j. So basically, if we're taking the derivative of this expression right here, say the derivative with respect to x1, that would be basically this beta 1 coefficient. If we're taking the derivative with respect to x2, that would be the beta 2. So again, what is the change in probability of y equals 1 over the change in xj for any of the independent variable? That is basically the coefficient beta j. So what we're saying here is, and how we are interpreting this coefficient is that for one unit change in x, we see beta units changes in the probability of y equals 1. So the nice thing about the linear probability model is that the marginal effects are the coefficients. And what these marginal effects are explaining, they're explaining the effect of the independent variable on the probability that y would be equal to 1. So by how much x changes, that would be by as many units as the coefficients on the probability of y equals 1. Okay, so now the marginal effects in the Probit and Logit models are a bit more complicated because we have a nonlinear function g. So this is the Probit and the Logit model, the generic form of it. So the probability of y equals 1 is equal to g of this expression here, x beta. So the coefficient on xj is still beta j. So basically the coefficient on x1 is beta 1, the coefficient on x2 is beta 2, the coefficient on xk is beta k. But now if we want to take the marginal effect of xj on the probability of y equals 1, we need to take a derivative. So the change in the probability of y equals 1 divided by the change in xj. So what we are doing here in order for us to find the derivative is we have to first take the derivative of this expression, which is g prime of x beta. So g prime of x beta, that will be the derivative of g of x beta. So here we have g prime of x beta, the derivative, times, then we go inside the expression, and the way to find the derivative is just basically take the coefficient on the x variable, and so that's going to be times beta j. So this is how we basically take a derivative. So now when we have the change in the probability of y equals 1 over the change in x, now it's no longer the coefficient. Now we have this function g prime of x beta, which is the derivative of the g function. So this marginal effect would explain the effect of the independent variable on the probability of y equals 1. So basically, by how much the probability of y equals 1 increases when xj increases by 1 unit. But now the problem here is we don't have the coefficients. We now have actually a function here that depends on x. We have seen this with the marginal effects when we have like squared variables or interactions of variables. So we have seen this before, but this is even more complex here because of the g function. So now let's talk about the specific marginal effects in the Probit and the Logit model. So here, this is the expression that we had on the previous slide. So changing the probability of y equals 1 over the change in xj. And that's going to be g prime of x beta times beta j. This will be the coefficient. So remember that for the Probit model, we have the probability of y equals 1. That's phi, the CDF of the normal distribution of x beta. And so the marginal effect is going to be the change in the probability of y equals 1 over the change in xj. And so if we take the derivative of the CDF, this capital 5, that's going to be the PDF of the normal distribution. That's just a property of the normal distribution. So this phi of x beta, that is the PDF of the normal distribution. Basically, that's the bell-shaped curve that I showed you earlier, and times beta j. So this is how this marginal effect is going to look like. For the logit model, this is the functional form of the logistic distribution. So we have the probability of y equals 1. We have the exponent of x beta divided by 1 plus the exponent of x beta. So if we take the marginal effect here, how we're going to take it is we have exponent of x beta 1 plus the exponent of x beta squared times beta j. So notice again, in both of these cases, we have the beta j coefficient being multiplied by another function of x beta. So now the problem is that there are many x's in the sample. There are as many x as we have observations I. And so at what point would we evaluate these marginal effects? And that's what we're going to do on the next slide. So we want to know at which x we want to evaluate this marginal effect. So there are two options. The first one is because the marginal effect here depends on x, we could calculate the marginal effect at the mean, which would be calculated at the mean value of x, so which is x bar. So how we have this expression here is we have the same expression as here, only that we replace this x with x bar. So here we have all of the x variables, they're the means of it. So basically, we have the average age in the sample. We have the average education. We have the average experience, and so forth. So this is how this marginal effects are going to be calculated here. It's going to be at the mean for each of these x variables from x1 to xk. Now, the average marginal effect would be calculated for each observation and then averaged across all the observations. So what this is doing is, you see like how here we have xi. So for each individual I, we would plug their x values of the independent variables, and then we would take the average of it. And so the average would be the same as the summation 1 over n, the summation of all of these over I, the g prime of x. So again, there are two ways in which to calculate these marginal effects. So the marginal effect is the mean. You take the average of x and then you plug it in, and that's how you estimate it. Or the average marginal effect is you take the marginal effects for everyone in the sample and then average those effects. That's what's called the average marginal effect. So the marginal effect here at the mean uses the means of the variable. So one of the problem is that there may not be such an average individual. So for example, if we have a certain average age for the person or average education, maybe there's no one with such education or such age in the sample. Or for example, if we have a variable that is female, obviously it's going to be equal to 1 for female, 0 for male, but a mean for such variable would be 0.3. So basically we would have that a person is 30% female, which does not make any sense. And so that's the problem with calculating marginal effects at the mean, because there may not be such a person for which these mean values make sense. Now, the average marginal effect makes more sense because we calculate the marginal effects for each person and then we average them. But in practice, we will see that the marginal effects will be similar, although not in every case, but oftentimes they'll be very similar. And another point that we're going to make here is how to calculate the marginal effect for an indicator variable. So now we have the model here of probability of y equals 1, and here we have d1, which will be an indicator variable. So notice our y is the binary variable 0, 1, but we could also have a binary or dummy variable here that is an independent variable. And so how would we calculate marginal effects for such a variable that's not a continuous variable? And how we would be doing this is we will be calculating the expression of g of this function where we would replace d1 with a 1. And then here we would be calculating the g expression where d1 would be replaced with 0 because these are the only options of 1 or 0. So here, this will be the marginal effect of d1 being equal to 1 instead of 0 would be the difference. This is basically the probability if d1 is equal to 1. And this is the probability of y equals 1 if d1 would be equal to 0. And so that's how we are going to be calculating marginal effects by taking the probability of y equals 1 if d equals 1 and the probability of y equals 1 if d1 is equal to 0. And this is how we would be calculating the marginal effect for an indicator variable that would only change from 0 to 1, and there's no other options for it to change. Okay, so here are the marginal effects as they're calculated. So we have the Probit marginal effects at the mean, then the Probit average marginal effects, and then we have the Logit marginal effects at the mean and the Logit average marginal effects. So we have now all four combinations. And unlike the coefficients that we saw, the marginal effects for the Probit and Logit models are similar. So if you look across all of these models, we have these marginal effects are actually very similar across the models. Now, we also have that the marginal effects at the mean and the average marginal effects are similar. So these marginal effects at the mean and these average marginal effects are similar, though in this particular case, they're not as similar. And it's probably because the sample size is very small. But here again, we have these marginal effects at the mean and the average marginal effects being similar, although again, not quite as similar. We see a difference here and we see a difference here. Actually, the Probit and the Logit models for at the means seem to be much more similar to each other than the average marginal effect. And again, these two seems the average marginal effect between the Probit and the Logit seem more similar than say the Logit marginal effect at the mean versus the average marginal effect for the Logit model. So the nice thing about using these marginal effects is that the magnitude of these marginal effects can be interpreted because again, they are the change in the probability of y equals 1 based on a 1 unit change in x. So how we are going to interpret this is that, for example, this marginal effect here of 0.051, we would interpret that for each additional year of education, we have that women are 5.1% more likely to be in the labor. We would have that women are 5.1% more likely to be in the labor force. So notice I underlined the word more likely. So we should always use the word more likely. And here for this one, if we have one additional child that is less than 6 years old, women would be 34.6% less likely to be in the labor force. So again, the word less likely. So notice how here we have more likely or less likely. And this again is coming from a baseline of, say, the unconditional probability that we saw 57%. So here we're saying if we know that this person that a person is one more year has one more year of education than another person, we know that for them they're going to be 5.1% more likely to be in the labor force. And if they have one more young child at home, they're going to be 34.6% less likely to be in the labor force. So this is how we interpret the marginal effects. Now we're switching gears to talk about goodness of fit measures. And before we talked about the R-squared as goodness of fit measure. So we don't quite have R-squared here, but we have a similar concept called pseudo R-squared for the Probit and Logit models. And the pseudo R-squared is also known as the McFadden's R-squared, and that's a measure of the goodness of fit for Probit or Logit models. And what it does is it compares the log likelihood of a model with that of only a constant. So the formula for that is that the pseudo R-squared would be equal to 1 minus the log likelihood of an unrestricted model with all of the independent variables divided by the log likelihood for a restricted model with only a constant. So here, this would be the log likelihood of a model, restricted model that only has a constant in it, so no independent variables. So basically, this is the poorest fit of them all because we have no independent variables. And hopefully, as we're starting to add on more independent variables, this log likelihood function would be increasing because we're trying to maximize this log likelihood function. So now, if the independent variables do not explain the dependent variable well, then the log likelihoods for the restricted model L0 uh, and the and and the log likelihood for the unrestricted model, they will be similar and the pseudo R-squared would be 0. So what we are saying here is that the log likelihood, um, if this is the log likelihood with no independent variables, and if this one is almost the same as the one that has no independent variables, then this divided by that would be equal to 1, so this expression would be equal to 0. So on the other hand, if the independent variables explain the dependent variable very, very well, here we would be having, when we're maximizing this log likelihood function, because that's a negative number, as we're maximizing it, it's going to be actually a smaller number close to 0. So if this is actually close to 0, what we're going to see is that 1 minus 0, we're going to be approaching a 1. So if again the independent variables are explaining the dependent variable very well, then we have the pseudo R-squared would be approaching 1. Okay, so the pseudo R-squared basically indicates how well the model predicts the outcome and how well a model improves on a null model that has only an intercept, but the magnitude is not interpreted. So how we can use the pseudo R-squared is that the higher pseudo R-squared that has the same dependent variable but different independent variables would indicate that the model predicts the outcome better. So again, if you have a model that has, say, 3 independent variables, same dependent variable, and if it has 3 independent variables versus 4 independent variables, and one of these models has a higher pseudo R-squared, then we should use the model that has higher pseudo R-squared if it's improving on it, or if we have like different variables, not necessarily the same variables, we should be picking up the model that has the higher pseudo R-squared. So now in our particular example, the pseudo R-squared would be equal to 1 minus the log likelihood for the unrestricted model versus the log likelihood for the restricted model with only a constant. So if you only have a constant and no independent variables, this is what the log likelihood function, this is what the log likelihood value is. And here, when we actually added independent variables and we started on maximizing this likelihood, we actually, that's how we maximized it. We got to minus 406.30. And so you see like how we started from this value and we maximized it to this value. And basically that's when we have a 0.21 as far as pseudo R-squared. So this pseudo R-squared shows how well the model predicts the outcome. And again, a higher pseudo R-squared is being preferred. A second measure of the goodness of fit is going to be percent correctly predicted for the Probit and Logit model. So percent correctly predicted would be a goodness of fit measure, which shows the percent of correct prediction to total predictions for the binary variable. So here we have the actual outcome y is 0 or 1. So basically either a person is in the labor force or is not in the labor force. So that's the actual outcome. The predicted probability P of y equals 1 would be a number between 0 and 1. And so if the predicted probability is greater than 0.5, we would say that y would be equal to 1. Otherwise, y would be equal to 0. So there are 4 cases of making correct or incorrect prediction. So either the actual value, it could be 1, or the actual value could be 0. So this is the actually the person working, and this is the person not working. And from our model, we can either have that the predicted value is a 1. We could either predict that this person is working, and we would do that if the predicted probability is greater than 0.5, or we would predict that this person is not working if the predicted probability is less than 0.5. And so here we have these 4 cases. So if the actual is 1 and the predicted is 1, that's going to be a correct prediction. If the actual is 0 and the predicted is 0, then we would have correct prediction. And this is an incorrect prediction when the actual is 0, but we predicted the person is working. And if the actual is 1, but we predict 0, that's also going to be an incorrect prediction. So the percent correctly predicted would be the proportion of correct predictions to total predictions. So what we're going to do is we're going to sum up these numbers here and this number here, and we're going to divide by the total number of predictions. And so here, the percent correctly predicted should have really high values. No one gives you a cutoff point, but these values should be very high number, like say above 70% or something like that. Because if you have in the data 50% working and 50% not working, even a very bad model could predict 50-50 of working and not working just randomly, right? So having a 50% correct prediction is not that good of a prediction in this particular case. So we want higher percent of predictions, correct predictions if possible. So in our particular example, after we estimate the Probit model and we could get the predicted values y hat, the table will show the number of correct predictions and incorrect predictions, and the total number of predictions is 753. So here we have these cases of the actual being 1 or 0, and here are the predicted values of 1 or 0. So the correct predictions are here and here, and these are the incorrect predictions. And so how we're going to calculate percent correctly predicted is we're going to sum up this correct prediction and this correct prediction divided by the total prediction. So if you sum up all these 4 numbers, that's the 753. And what we're going to get here is 73.84. So basically for the Probit model, we have 73.84% of the outcomes are correctly predicted, which means if there were a 1, our model is predicting a 1. If there were 0, our model is predicting a 0 right here. And here is where the model did not do very well. Now for the Logit model, just quickly, though I haven't shown you this table here, we have, this was the correct prediction, this is the correct prediction. These are, again, the total number of observation. We have identical number because notice here, we have one less correct prediction here, but we have one more correct prediction here. So actually this plus this is happens to be in this particular case exactly this plus this, and that's why we have the same percent correctly predicted for the Probit and the Logit model. So that does not have to always be the case. So again, these were the 2 goodness of fit measures, which included the pseudo R-squared and the percent correctly predicted. Now, as far as review questions, go ahead and describe and give examples of a binary dependent variable. Explain the functional forms for the linear probability model, the Probit model, and the Logit model. How are the coefficients interpreted? Describe the marginal effects at the mean and the average marginal effects. How are the marginal effects interpreted? And describe the goodness of fit measures for the Probit and Logit model. So this concludes the presentation on the Probit and Logit models.